All right, so here's number 2 on the Chapter 12 review. So you've got this solid uniform sphere. It's got a radius r and a mass m. It's got a rotational inertia about a diameter of 2/5 mr squared. It is important to note that that diameter is going to run through your center of mass, right? And then it says a light string of length 3r is attached to the surface, and it's used to suspend the sphere from the ceiling. Its rotational inertia about the point of attachment to the ceiling is blah, 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 blah. So we're trying to find that. Okay? So this is really just the parallel axis theorem. The string itself doesn't have any rotational inertia because it doesn't have any mass. So really, it's just this. So the rotational inertia of the sphere about the ceiling is equal to the rotational inertia of the sphere about the center of mass plus mh squared. Okay? Now remember, well, so let's see. So the rotational inertia of the sphere about the center of mass is this guy, 2/5 mr squared plus mh squared. Now remember that h is how far your pivot point, your axis of rotation got moved. So our center of mass is here, right, at the center of the ball. Okay, oops, it's a glare, sorry. Our center of mass is there, and our new pivot point is here. So the pivot point actually got moved r plus another 3r. So it's 4r. Okay? So m times 4r quantity squared. So 2/5 is 0.4 mr squared plus 4r squared is 16r squared. So 16 mr squared. So add it up and you get 16.4 mr squared. Okay. Please make sure you know this parallel axis theorem. It is super important. The big thing to remember is that you can only use the parallel axis theorem if you know the rotational inertia about the center of mass. Okay. And then the h is just how far your pivot point got moved from that center of mass. Okay. There we go. Nice quick one.